Welcome everyone. So in this video we'll continue with vector algebra. When we talk about a vector, we should know few more terms. So the first one is a position vector. Then we should also know about the direction cosines and direction ratios. So direction cosines and direction ratios. Now before going into this, let us see what is a position vector. So in the previous video we have discussed vectors are used to analyze a three-dimensional body. So this is my x-axis, this is my positive y-axis, this is my positive z-axis. So I cap, j, k. These are the directions for x, y and z-axis, I, j and k. Now when I have a point here in the three-dimensional space which is connected by a vector, this is denoting the position vector. That is, this denotes the position, the location of a particular body. So this is a position vector which denotes the position or location. Now it is given by OP. Maybe if this is the origin O and if this is P, then OP vector can be written as xi plus yj plus zk, where x, y and z are the components along the x, y, z axis magnitude, and I, j, k are denoting the direction. So this is the component of that here, x, y, and you will correspondingly have it in z. So the theta or angle would be, this is alpha, this is beta, and this is gamma. So this is your position vector. Now direction cosines. Now from the diagram you would have seen, you can find cos alpha, cos beta and cos gamma. Cos alpha, cos beta and cos gamma. These are your direction cosine, which is also denoted by L, M, N. Now this components or cos alpha, beta, gamma is utilized to find the magnitude in the corresponding axes. So for example, if I would like to find my x coordinate, if this is a position vector r vector, and if I like to find what is that magnitude along the x coordinate, my x is equal to r cos alpha. How did I find this? Let me just draw this along the x-axis alone. So this is my r, this is my x component, this is my alpha. We have just used basic trigonometry. So cos alpha is equal to x by r. So x equal to r cos alpha. The same way, if I represent this along the y-axis, it will be like this. This is my y component. This is beta. This is y. This is again r. So cos beta is equal to y by r. So y is equal to cos beta. So we can have y is equal to cos beta into r, and z is equal to r cos gamma. So cos alpha, cos beta, cos gamma can be represented as L. So my x is equal to LR, y equal to MR, z is equal to NR. Now this LR, MR, NR are called as your direction ratios. Now these are your direction cosines, which is just the cos you are finding. So the name itself suggests that. Whereas direction ratios, A, B, C are the magnitude along that respective axis. As you can see here, the direction ratio talks about the direction alone. What direction? That is what is the angle you make it with the x-axis. What is the angle you make it with the y-axis? So cosine talks about how much you have when you are a unit vector. Whereas A, B, C are your direction ratios, which talks about how much exactly you have. That's why when you square L square plus M square plus N square, you will always end up with 1 because it is respected for a unit vector. We have assumed that if it is a unit vector, what will be the value? Whereas a square plus b square plus c square need not to be 1 always. Right? This is always 1. So this is about your position vector, direction cosines and direction ratios. So next we'll see how to add and subtract two vectors. So let us take this condition. That is a water bottle on the surface. Now this water bottle is taken by one of the student, person 1. Person 1 takes this water bottle and brings it here. So now the water bottle has moved to a position. Now the person 2 who comes sees that, oh, why this water bottle is here, and he wants that to be exactly in this position, and he moves back the water bottle. So what happened to the bottle? There was one force that acted here which made it to move here. Now then there is another force which acted and that moved the water bottle to the initial position itself. So now when I add these two vectors, their net effect is 0 because the water bottle has come to a place where it was already placed. So where it was already placed. So the net effort of this is 0. So this is how a vector addition could be related. Now if there is no net movement from the initial position to the final position, then the sum is actually 0. So let us consider this case. You might have seen the famous comedy from the movie Kalagalappa, where the person asked to place the Parjimutta in different places. Right, the same case here. So I have a body which is here. This is initially moved to a position here. So this is my vector 1. Now there is one more force that acts here, which brings it here. This is my vector 2. Now there is third force which acts and bring it here. This is my vector 3. Now the net effect is the addition of these three vectors. So what has happened to the body? We will not worry about what are the vectors. Rather, what has happened to the body is our prime concern. So initially it was here. This is my position 1 and this is my final position. So the net effort that has created is just this. So this is my resultant of these three. Resultant vector. So this is the simple concept for addition of two vectors. So how we will add it? We will just have, for example, let me take AB vector. So this is how we represent a vector AB and this denotes it is a vector plus BC vector, right? When we have AB vector like this is AB vector. If this is BC vector, then my resultant is technically this. This is AC vector is equal to AC vector. So you can just draw it pictorially and find it. So this is the addition of vectors. So we will try also to subtraction of vectors. Now to subtract, let me take two vectors here. This is my A vector and let me take this as my B vector. Now subtraction is actually A vector plus negative of B vector. So this is actually A vector minus B vector. So what I'm going to do is I'm going to add the negative of B vector with A vector. So I'll draw A vector first. This is my A vector. Now this is my B vector. If I draw, this is actually my B vector, but I need negative of B vector which will exactly follow the same. We call this as line of action. So it will act along the same line. Only thing is it is in the opposite direction for the same magnitude. For example, if this is 3 centimeter, if you are representing the magnitude as 3 centimeter line, this should be a 3 centimeter line. Now this is minus B vector. Now my resultant will be, I was here, now I am here. So this is the resultant. This is what the vector has created. So this is my output. So this is A vector minus B vector. Now, what happens when you multiply a vector with a scalar? So, I have a vector, which is of magnitude 2. Now, if I multiply this with a scalar, maybe 5, then my vector actually increases. The direction remains same, whereas the magnitude of the vector increases. So, lambda, we simply write it as lambda a vector. Now, what happens if you divide? It will also the same, right? It will proportionally reduces. For example, if I divide this by 2, my vector will become 1, magnitude of 1, which is acting in the direction, the same direction. So this is about your vector addition, subtraction, and what happens when you multiply it with the scalar. When you multiply it as a vector, it is altogether a different case, which we'll be learning in the later stages. We'll go ahead with the next concept. Vector addition is always commutative. So a vector plus b vector plus c vector is also equal to b vector plus c vector plus a vector. Now let us take the same condition. I have a body here. I have, let us say I have three vectors. Let me represent the three vectors. This is vector 1, which is a vector. This is vector 2, this is b vector. And this is vector 3, which is c vector. Now all are magnitude in the equal and their directions are already mentioned. So now let us assume that I follow this order. So my body moves here, goes here and comes down. So this is my final position. So this is my initial position. This is my final position. Now let me try doing it in the different order. So this is my body. Now I have B first. So this acts first. Then I'm going to have A. This goes top. Then again it is going to come down because it is C. So this is my initial position. This is my final position. It is same as the previous case. So let me try the different order. This is my body. Now I'm going to have C first, then B, then A. Still, I have started at a particular point. My final position will be exactly along the same line on the right hand side for the same distance of magnitude, whatever this magnitude is, right? In all the cases. In all the cases, it is just the magnitude of V that is displaced. So, irrespective of the order you take, vector addition can be giving you the same result. So it is a commutative. So you can have any order because we care about the initial and the final position. Now how to find the vector? For example, again, let me have a condition. We have A1, which is the position 1 of a particular condition. Then we have A2, which is here. So this is X1, Y1, Z1. This is X2, Y2, Z2. Now I need vector A1, A2 vector. How to find it? So let us define the position vector of these two first. So this is X1I plus Y1J plus Z1K. This is X2I plus Y2J plus Z2K. So I need this vector A1, A2 vector. So this is the direction. Now if you are trying to do it with the help of vector addition, now this is my A vector. Let me take this as my B vector. Let me take this as my C vector. Our position vector, we write it as OA1. So my A vector is OA1. My B vector is A1, A2 vector. So I'm just doing vector addition. This plus this. So I move from here, then I move here is equal to when I move from here to here directly. So is equal to OA2 vector. So my A1, A2 vector is equal to OA2 vector minus OA1 vector. So this is how I could find. So generally we'll write it as AB vector is equal to OB vector minus OA vector. So this is how you could find the vector of a given 2 points. So vector between 2 points.
With this, we'll try to find the addition of two vectors. Now, what we have learned in the previous case was a graphical method. Now, we'll try to use the analytical method here. Let me take 2 points. point A, which is 3, 2, 1, point B 6, 7, 3, and point C 1, 2, 4, 6. Now this is my A. Let me take this as B. Let me take this as C. So my AB vector is this. My BC vector is this. My resultant is my AC vector. Now to find this, I am finding the addition of two vectors, that is AB vector plus BC vector. Let me find this. So to find AB vector, I should find OB minus OA vector. That is my position vector this minus my position vector this, which is 6i plus 7j plus 3k minus 3i plus 2j plus k. This will give me 6 minus 3 is 3i, 7 minus 2 is 5j, 3 minus 1 is 2k. The same way, my BC vector will be OC vector minus OB vector as the position vectors. So 1 minus 6 minus 5i, 4 minus 7 minus 3j, 6 minus 3 is 3k. So these are the AB and BC vector. Now if I have to add it, it is just AB vector plus BC vector, which is equal to 3i plus 5j plus 2k plus minus 5i minus 3j plus 3k. So if I have add the corresponding components, 3 minus 5 is minus 2i, 5 minus 3 is 2j, 2 plus 3 is 5k. So this is the answer when I add two vectors directly. Let me try using the position vector here if I go from A to C. So if I need AC vector directly, this is my AC vector. Now if I try to find my AC vector directly from the coordinates, my AC vector is equal to OC vector minus OA vector, which is equal to 1 minus 3 minus 2i, 4 minus 2 plus 2j, 6 minus 1 plus 5k. So this is the answer. As you can see, the answer for both the cases are same. So either you can find using the graphical approach, which you will not be following in the questions that you are going to have. You will be following the analytical approach, where you could either use this approach of directly using the position vectors, or you could find AB vector, BC vector and add it. If it is subtraction, AB vector minus BC vector could be done to get the answer. So this is the analytical approach to find the addition and subtraction of two vectors.
The next one is scalar and vector components of a given vector. So let us take a vector. A vector is equal to 5i plus 6j minus 10k. Now the scalar component talks about the magnitude alone. It will not have the direction. So my scalar components are 5, 6, minus 10. So these are my scalar components. Now when I find the vector components, it is along with the direction. So 5i is my vector component, 6j is my vector component and minus 10k is my vector component. So you have to write it separately because we are writing the x, y and z components separately. Now we'll go ahead with unit vector once again. We have seen what is a unit vector in the previous video. So here we will be seeing how to find the unit vector of a given vector. 10i plus 6j plus 3k. So how to find the unit vector? Now what is a unit vector which doesn't have a magnitude? Its magnitude is 1 and it has a specific direction. So when I would like to go in the same direction as this vector, I should know in what direction this vector has traveled. So to find that, we'll use a formula A cap. This cap denotes that it is a unit vector and this denotes that it is a vector, A vector. So is equal to, I have my A vector but I don't want the magnitude, I just want the direction. So I would like to remove the magnitude divided by the magnitude of this vector. This is the magnitude alone of a given vector, magnitude. So how to find this magnitude of a given vector? So when we try to do it, magnitude of a vector is equal to root of x component square plus y component square plus z component square. So this is how you could find the magnitude. This is the formula, and this is simply derived with the help of Pythagoras theorem.
So we'll try to do this sum where we have been asked to find the magnitude of the given vectors. So let us do these two and you can try this. So magnitude of a vector for case 1, we know the formula, it is root of x square plus y square plus z square. My x component here is 1, y component is 1 and z component is 1. So it is root of 1 square plus 1 square plus 1 square. That will eventually be 1 plus 1 plus 1, which is root 3. For my case 2, it is root of 1 by root 3 the whole square plus 1 by root 3 the whole square plus minus 1 by root 3 the whole square. You should be careful here. My formula is x square plus y square plus z square. So I have added plus in between. My z component is minus 1 by root 3. So I have taken the minus inside, which will eventually will become 1 by 3 plus 1 by 3 plus 1 by 3, which is root of 3 by 3, which is root 1, which is equal to 1. So this is the magnitude. So technically, this is a unit vector because the magnitude of this vector is 1. So we have to find the scalar and vector components of the vector with initial and final points as follows. So instead of giving us the vector here, the points are given, right? So this is our vector. So this is our initial point and this is the final point. This is given. We have to find the scalar and vector component. Now to find this, in case this is AB vector, so this is my OA and this is OB. That is the position vector. From my respective 0, 0, 0 point, this is my position vector OA vector and this is my position vector OB vector. And my AB vector is equal to OB vector minus OA vector. This is what we have learned. So my OA vector is, since there is only two components, it is 2i plus j, and my OB vector is minus 5i plus 7j. So I have to find my AB vector first. So my AB vector is equal to OB, that is minus 5i plus 7j minus plus 2i plus j, which is equal to minus 5i plus 7j minus 2i minus j, which is minus 7i, j and j we will add it, so plus 6j. So only the like terms, like the algebra where you will add the like terms, here you have to add the like components, I and I, j and j, k and k. So my scalar components of this is minus 7, 6. Only the values which is there with j and I, and my vector components are minus 7i and 6j. We have to add a comma because we are writing the components separately. So this is x component, y component, x component, y component. Because there is no z component here, this is a two-dimensional representation. The same way you could try doing this. Now find a unit vector. So you have to find a unit vector which has only the direction. The magnitude will be 1. So you have to find the unit vector which is in this direction. So this vector, in case if this is the vector, which is a vector, the unit vector that I'm going to find should be also along the same direction. This is what is the intention. Now we know the formula for unit vector. A cap is equal to a vector by modulus of a vector. So to find modulus of a vector, we should find it using the formula root of my x component is 1, y component is 1, z component is 2. 1 square plus 1 square plus 2 square, which is root of 1 plus 1 plus 4, root 6. So my a cap is equal to I cap plus j cap plus 2k cap divided by root 6. This could be even written as I by root 6 plus j by root 6 plus 2k by root 6. This itself is fine. So this is how you could find the unit vector for a given vector. Thank you. Happy learning.